Hello everyone, we are Team Stitch, which stands for Suture Tensiometers Improving Teaching Capabilities in Hospitals. We will be innovating the common needle driver to include tension measurement capabilities. Currently, surgeons spend years practicing their suturing technique to develop a feel for the correct amount of tension they should use when closing a layer of tissue. There is a need to define this feeling with a metric of tension. A standardized amount of tension will improve the quality of the suturing process, especially for newer surgeons, as well as limit the risk of infection from improper wound closures. Our device that we create needs to function as a normal needle driver, be capable of reading out an accurate tension measurement, be reusable, and not interfere with the suturing process. Our target market will begin with the research industry at first, with teaching hospitals all around the United States. Once the tension measurement is standardized, this device can be used to teach over 21,000 medical students each year and will eventually move into being used in all surgical divisions in every hospital.
Our approach to the issue was to build a casing around the already existing needle driver. This casing will be lightweight and will not change the suturing process for the surgeon. Within the casing will be a force sensor resistor that will sense the applied pressure when the surgeon pulls on the suture line. The data from the sensor will be transmitted to a laptop that the surgeon will be reading off of to see the tension they are pulling. The wireless data transmission will be done through an Arduino receiver and transmitter system. The sensor and the Arduino system will be in the casing along with a LiPo battery to power the system. To save on cost and time, we 3D printed our casing. More specifically, we used a TPU filament to print the case with. The flexibility of TPU allows the pressure from the surgeon's fingers to be felt through the casing while also having an extremely high wear resistance. There are two parts to the casing, a top and a bottom, and they will latch together around the needle driver with the electronics encased inside. On this slide, you can see a close-up view of the electronic components that go into the device. The main part of the system is the FSR or force sensor resistor. From this sensor, we will get our data that will be shown to the surgeon. This data is sent wirelessly from the system to a laptop for the surgeon to read off of. This wirelessly sending of the data is done via an Arduino transmitter and receiver. For these components to run, they need to be connected to an Arduino board, and we chose to use an Arduino Beetle because of its small size. To power these components, we went with a LiPo battery because a LiPo battery is rechargeable and this will in turn prolong the device's lifespan. You can also see that there's an on and off switch attached to the circuit. This will allow the surgeon to turn the device on and off to save battery life. All of these components have been soldered together and will be going inside of our 3D printed casing.
When the device is being used, the doctor will be able to see in real time on a monitor in front of them the amount of tension that they are putting on the suture line. The delay between the pressure applied and the number appearing on the screen is roughly 1 second, and the number will be accurate to 2 decimal places. This accuracy will play a huge part when the device is used in researching the perfect suture tension. Through a series of verification and validation testing, we got results showing that the data being displayed was very close to the pressure being applied. This demonstrates that our device will be accurate when used in a clinical setting. You can see on the graph that when we were testing different pressures and weights on the sensor that the readout was very accurate with a standard deviation between 0.05 and 0.12. Moving forward, the future steps for this device would include miniaturizing the electronic components even further and increasing their accuracy and speed. With a higher budget, the casing surrounding the needle driver could be printed with a higher quality filament, which would increase user comfort. We would like to acknowledge and thank our mentors, professors, and TAs for all of their